In this video, we will talk about correlation. Correlation is a very general term that merely means association between variables. However, here we will be using it in a much narrower sense. In particular, here we are concerned with associations between two quantitative variables, although correlation can be used more broadly. And in fact, we will only see the calculation of a specific type of a correlation index. The idea behind correlation is that we have two measured variables for each entity under study. For example, we have two different scores for each child. Each child is measured with two different tests, or each child is measured in two different time points with the same test or any other kind of combination. So each entity has one value for each of two variables. And in this case, we can calculate indices of association. In this video, I will show you how we calculate the most commonly used parametric index of association. Let us start by looking at a scatter plot where the relationship between two quantitative variables becomes visually obvious. This is the case of vocabulary as a function of age for children. Each data point here corresponds to one child. On the horizontal axis is the age of the child in months, and on the vertical axis is the raw score on a vocabulary test. We see that these variables are correlated because none of the younger children have very high scores, and there are very few of the older children that have very low scores. So scores show a relationship between age and vocabulary, which is understandable because children between the ages of 4 and 8 develop rapidly their vocabulary as they learn more and more words. So it's only natural that 8-year-olds know more words than 4-year-olds. Still, the relationship is not perfect as there is a wide range of performance for each age range. And here is an example of two uncorrelated variables. This is height as a function of age for adults. Each point again is one person. On the horizontal axis, we have age in years, and on the vertical axis, we have height in centimeters. Because people don't grow anymore when they're adults, these two variables are uncorrelated, and we see that the range of heights is about the same for the different ages, except that there's more participants in the younger ages here because this was a student sample. But this is not an association between the two variables. To be able to see clearly the steps that are involved in calculating a quantitative index of association between two quantitative variables, it's easier to use a simulated data set. This is an artificial data set composed of 30 points. You can imagine that there are 30 children who are measured on two variables, so two kinds of tests. On the horizontal axis is the first variable, the first test, and on the vertical axis is the second test. So here is one child who received about 27 on the first test and a bit over 2 in the second test, for example. As you can see on the axes, these are the raw scores. The first thing we want to do when we want to calculate the index of association is to calculate the z-scores, so standardize these values. These are the standardized scores. Obviously, the scatter plot is exactly the same. We didn't change anything about the relationship. We just transformed the scales of the two variables so that now both variables have a mean of 0 and a standard deviation of 1. But there is nothing different about the relationship to one another. Let's see this once more. I'm going to go back to the raw data. The axes change, and now back to the z-scores. And it's exactly the same scatter plot. So we have retained the exact same relationship among the two variables, but now are working with numbers that have a mean of 0 for each variable and a standard deviation of 1. Let us make these points a little larger so that they're easier to see and number them so we can identify each one. And then add a line for each mean. These are the means, and because these are now z-scores, the means are exactly on 0. Let us consider a specific data point. Let's say data point number 4. This data point has a value on the y variable on the vertical axis, which is equal to its distance from 0. And this value is, in fact, its z-score. So the distance of this point from its mean of 0 is its z-score. That's what we achieved by standardizing both variables. And likewise, its distance from its mean on the other variable, on the first variable, is again its z-score on that. So z for x and z for y. For this child, the value on the y variable is above the mean. In other words, it is positive. It's above 0 since it's a standardized value. So this is a positive z-score. For the first variable on the x-axis, this child has a value that is lower than the mean, so it is to the left of the line. Therefore, this is a negative z-score. If we multiply these two scores for this one child, so multiply z of x by z of y, we will be multiplying a positive by a negative number. And the product of a positive with a negative number is always a negative number. Plus times minus equals minus. And for all these 7 points that are in the top left quadrant, which have a positive z-score for y and a negative z-score for x, the product of their two z-scores will always be negative. Let's see what happens with point number 23. Again, these are the z-scores for this point. They are the distances from the mean of 0. And in this case, both z-scores are above 0. This point is above the mean for both variables. So this would be a positive number, and this would be a positive number. If we multiply these two z-scores together, the product of two positive numbers is always a positive number. Plus times plus equals plus. And the same will be true for all of these 11 data points in the top right quadrant. So the product of the two z-scores for the two variables for all of these points will be a positive number in this quadrant. Thinking in the same way, we can easily see now that for these 4 points in the bottom right quadrant, which are above the mean on x, but below the mean on y, these points will have a positive z-score on this dimension and a negative z-score on this dimension. So the product of their z-scores will be plus times minus equals minus. For all 4 of them, it will be a negative number. And finally, for the 8 data points that are in the bottom left quadrant, we will have a positive product because for these points, both variables are below their respective means. So both their zx and their zy will be negative, and the product of two negative numbers is positive. So we have in total 11 data points with negative products and 19 data points with positive products. So if we add all of these together, we expect the positive ones to win, and so that the total sum will be positive because there's more of them. And it's not just that there are more, but also there are some that are farther apart. So this is farther from 0. This has a large negative zx. This is far from 0, and this relatively far as well, whereas most of the negative points are nearer 0. So these are the points that are near zero, and there are more positive points far from zero than there are negative points far from zero. So the positive ones are expected to win if we add them all up, not only because there's more of them, but also because some of them are much larger. The sum of these products of z-scores is leading us toward an index that is called a correlation coefficient. So to calculate this kind of a correlation coefficient, what we do is we calculate the standard scores for one variable, that's zx, the standard scores for the other variable, that's zy, and for each entity, so for I from 1 to n, where n is the number of children in this case, we multiply the two standard scores for the two variables for each participant, and then we add all of those products up. And so this is the sum of the products of the standard scores, and we normalize this by dividing by n minus 1 to get a sort of average. It's not exactly their mean, because in the z-scores, we've used the sample standard deviation, which also has an n minus 1 in the denominator. If we used the formula for the population standard deviation with an n in the denominator, then we would have used n here as well to balance that out. But using the usual kind of standard deviation, as we always calculate from samples, this requires an n minus 1 in the denominator for things to come out as they should. This is called R, and it's the Pearson's correlation coefficient, and is the index of association for two quantitative variables that is most often used. This index has the property that its magnitude ranges between 0 and 1. If the two variables are completely unrelated, R will be 0. If the variables are perfectly related, so that you can completely predict one from the other with no error at all, then R would be equal to 1. Of course, in practice, we never get values that are either 0 or 1, but the value ranges between 0 and 1, and the higher the correlation, the stronger the association. However, R isn't always positive, because it's possible for the negative products to win out if there are more points in the top left and bottom right quadrant, unlike the example we used here. So R actually has either a positive or a negative sign, indicating either a positive or a negative relationship. As you recall, a positive relationship is when high values on one of the variables are associated with high values on the other, whereas a negative relationship between two variables is when high values in one variable are associated with low values in the other variable. So what is our index of association for these example variables here? What is R? This is our simulated data set that we're working with, and R for these data points turns out to be equal to 0.46. This looks like a medium-sized correlation or a moderate correlation. Let's look at some other examples to see what different values look like. Here is another simulated data set where there doesn't seem to be much of a relationship. There doesn't seem to be any relatively empty quadrants here. The scatter plot indicates basically just scatter. Indeed, the R for this data set is only 0.16. This is a very low value. In contrast, in this example, the variables seem to be relatively strongly associated, as there are essentially no data points in the bottom left and top right quadrants. Although there is still substantial scatter, it's mostly confined to the top left and bottom right. And the R for this data set is minus 0.72. It's minus because the relationship is a negative one. High values on X are associated with low values on Y, and high values on Y are associated with low values on X. Here's another example with an even stronger association. Here, this is a very narrow band of points that go from top left to bottom right, whereas most of the panel is empty. This is an extremely strong correlation. Indeed, R is equal to minus 0.96. Minus because obviously this is a negative relationship, and 96 is almost 1. We practically never see such numbers in our field. The only way to get a correlation of 0.96 is to have a very reliable test and administer the exact same test twice. And in that case, it would have to be a positive correlation because high scores would be associated with high scores. Finally, just for illustration, this is what a perfect correlation looks like. All the points are on a straight line. In this case, R is equal to 1. This absolutely never happens with real data. The only way to get R equal to 1 is to calculate the correlation of one variable with itself. So let us now go back to our simulated data set with R equals 0.46. Is this a statistically significant correlation? What does this question mean? Let us think of the null hypothesis. The null hypothesis states that we have sampled our data from a population in which there is no correlation between these two variables. So R in the population is equal to 0. That's the null hypothesis. The alternative hypothesis is that R in the population is not equal to 0. So how can we evaluate 0.46? What we need to do here is we need to sample from the null hypothesis, derive the sampling distribution for R when R in the population is actually 0, and then see how likely it is to obtain an index of 0.46 or greater in magnitude from sampling from the null hypothesis. And this is the sampling distribution of R for sample size of 30 when there is no correlation in the population. So this is drawing sets of pairs of random numbers which are uncorrelated. And for sets of 30, calculate R of these random numbers, and then plotting the histogram for R for 100,000 samples of that sort. You see that it's possible, and sometimes we do get substantially high values for R. So even 0.6 is possible, but it's not very likely. It's possible to get a correlation in a sample of 0.6, even if there is no correlation in the population just by sampling error. This is the same kind of thing we've seen before with different kinds of indices by sampling from the null hypothesis. Now, what is the probability of these high values? Let us indicate our actual obtained value of 0.46, and we're going to do it on both sides because a value of 0.46 and a value of minus 0.46 are equally likely or unlikely when sampling from the symmetric null. The proportion of samples that have such values or farther from 0 for R when sampling from the null is actually quite low. It's 0.5% on each side. So in total, the p-value for our R of 0.46 with 30 data points is 0.01. It's 1%. This is lower than the conventional limit of 0.05, and therefore we can conclude that there is a statistically significant correlation between the two variables in our sample. We reject the null hypothesis that R equals 0. So that's how we calculate Pearson's R, and in this case can conclude that our two variables are related. However, we should be very careful before we actually rush to a conclusion, because there are a number of assumptions that lie behind this calculation and need to be checked before we can even report this R. The main assumptions that we have to make sure are not violated are linearity and normality. Linearity concerns whether the relationship between these two variables is close to a straight line and it's not curved in any way. That's because what Pearson's R actually computes is the degree to which the two variables are in a linear relationship. R always means that. R means the degree to which the two variables are in a linear relationship. So a low R doesn't mean that the variables are unrelated. It means that they have a small linear relationship, or a very small or a non-existent one. But because we want to interpret R as a measure of relatedness more generally, R is actually misleading and inappropriate when the relationship between the two variables is not linear. So in those cases, we use different indices. Let's see a couple of examples. Here is an example of a nonlinear relationship where we have a negative relationship between the two variables for low values of x. Low values of the variable on the horizontal axis are in negative relationship with values in the other variable, but for values above 20, there is essentially no relationship. It goes a little bit like that. So if we calculate R for this pair of variables, which is inappropriate, we would obtain a value of 0.64 minus 0.64 because it's negative. But what this number is actually evaluating is the relationship along a line, a straight line. This number indeed indicates the relationship along this line, but this is not a good approximation to the actual relationship between the two variables, which looks a bit more like that. So this is a case where we should not be using R. Another case is an even more egregious departure from linearity, in which the relationship is not only nonlinear, but is also non-monotonic. What is a monotonic relationship? Monotonic is a relationship that doesn't change direction. In this case, the relationship is positive for low x and negative for high x. And then who knows what happens for values beyond these ranges. So it's going up and down. A monotonic relationship cannot go up and down. It can go up and then stay at some level and then go up again, but it cannot go down. Or the opposite. It can go down or stay at the same level, but it cannot go up. In this case, R equals minus 0.02. This is essentially a zero value, indicating absolutely no linear relationship. But as we can see, this is misleading if it is interpreted as no relationship, because these variables actually have a very strong relationship, and you can predict the y value quite well if you know the x value. The second assumption is normality. What is actually required for R to be interpretable in the intended way is that the two variables are in a bivariate normal distribution. This is not so easy to examine except visually, so that's a very good reason to look at scatter plots. But what we can do first is look at the prerequisites, which concern the normality of each of the variables, which we know how to do, and also check that there aren't any significant outliers. Outliers are data points that are far from the rest of the distribution. And in fact, we shouldn't have either univariate outliers, that is, outliers that are far from the distribution on one of the variables, or bivariate outliers. So we shouldn't even have outliers that are far from the joint distribution. Let's see how that looks like in a scatter plot. Let's start with the simpler case where we have two variables that are not normally distributed. So on the left, we see the histogram and QQ plot for the X variable, and we see that's clearly not normally distributed. And on the right, the Y variable is quite similar. The scatter plot for these two variables looks like this. We see that most values are concentrated on the low left corner, the lower left quadrant, and there is a lot of scatter elsewhere. We should not be calculating a reporting in R for this combination of variables. Here is another case where we have univariate outliers, that is, data points in one of the two variables that are far from the distribution. As you see, these data points here are quite far from the rest of the distribution of this variable. Although the rest of the distribution doesn't look particularly bad, or the other variable doesn't either, these points actually distort the relationship because they're out here. So these two data points are well outside the bivariate distribution, are far from this blob of other points. If we calculate R for this data set, we see that it is 0.58. And if we remove these two outliers and calculate R without them, then we see that the relationship is 0.62. So these two data points have a rather large influence on the value of the R index. And it's not clear how we should be interpreting this. So the case with these outliers is one case where we should not be reporting the R index. And finally, in this example, both variables are reasonably normally distributed. But if you see their scatter plot, you see that there are a couple of points that are outside the main blob of other values. So although these values aren't outside the range on either variable, their combination of values for the two variables is very unusual. They stick out. This is what we call bivariate outliers. So they're outliers because they lie outside the distribution, but they're only bivariate outliers. They don't lie beyond the distribution on one of the variables. They lie outside the common distribution of the two variables as we see it here in the scatter plot. And if we calculate R for this data set, we see that it's 0.67. If we remove the two outliers, the two bivariate outliers, just delete them and calculate R without them, we see that it becomes 0.76. That is a very large difference. So it's not clear how the R should be interpreted for this data set. And this is another case where it is inappropriate to calculate. If we are careful about checking our assumptions, then we can use Pearson's R correlation coefficient as a very useful and commonly seen index of association between two quantitative variables, which can also serve for hypothesis testing by deriving a p-value and using that to either reject or not reject the null hypothesis.